Greetings everyone. I am Ali Kalakish. I am an assistant professor at the Lebanese International University School of Engineering. Today I will be presenting the paper Coverage and Cell Capacity Optimization in Private LTE Network based on position and expected channel knowledge. This paper is done by my former students Hamad Bakir and Riyad Youssef as part of their master thesis project. Here are the outline of the presentation, and we will start with the introduction. LTE and its faster version, LTE Advanced, is the technology behind 4G cellular networks. In fact, for the air interface, the main technologies used are the OFDM for modulation, OFDMA for multiple access, and MIMO to take advantage of the channel diversity. As for the core network, we can say that LTE is a pure packet switching network or all IP network. LTE is a worldwide success story. According to GSA January 2022 report, we had almost two-thirds of mobile users connecting through LTE. So this amount to 6.6 billion subscribers in 2022. As with all public networks, traditional LTE networks suffer from congestions and latency, especially during major events. So events where we have large crowd of people that are gathering together, like concerts and sport events in stadiums, may overload the network. Also, security situations or emergency situations where many people are trying to connect at the same time may also overload the network. Also, as with all communication over the air, traditional LTE may suffer from security vulnerabilities. So, to provide a solution for these problems, private LTE networks were proposed. Some advantages of private LTE networks over traditional LTE networks are: private LTE networks are more reliable and they have consistent connectivity even during rare events that may overload a network, simply because they are sealed from the general population. In private LTE networks, we can prioritize certain types of traffic, so providing a better quality of services for some application. Also, we have better and improved security. This can be done actively by using proper encryption technique in private networks, or passively by applying the concept of security by obscurity. As private LTE network, they have some parameters that are hidden and no one knows about them. Possible users for private LTE networks are the public sectors like police, fire department, healthcare departments, and other sectors. Also, defense and security agencies can use private LTE networks, smart grids also, and large corporation enterprises. Private LTE networks are built using known and mature technologies that can be optimized and designed custom-tailored according to the application and intent of use. As a problem statement, the main problems that we are going to tackle in this work is coverage and capacity optimization in the context of private LTE network. The optimization is studied in the context of a single LTE cell, and we consider that the inter-cell interference is negligible. As a private LTE network, we have no privacy concerns or restrictions concerning the tracking of user locations. So we consider that the users are employees in a organization or a enterprise, and they have to update their position regularly, and we consider that the network know perfectly their position. The knowledge of the user position within the LTE cell infers the knowledge of the expected channel. So that channel is considered to be constant on average at certain positions. This information is going to be used in the optimization procedure. The traditional approach for the optimization of LTE networks is done according to the optimization criteria. So for example, we have optimization over the coverage, optimization of the capacity, and quality of service optimization. For the coverage optimization, the focus is on optimizing some parameters such as RSRP, RSRQ, and SINR. This is done by surveying a location, doing a drive test, and some data analysis after that. Of course, at the end of this procedure, we have some recommendation like increasing the power, tilting the antennas, or other recommendations. For the capacity optimization, for example, we can improve the overall throughput of a system by proposing better scheduling algorithms. As for the quality of service optimization, we take into account the quality of service requirement of some application within the LTE network parameter as well. For example, like taking into account the delay, and this concerns the delay-aware quality of service optimization. So the proposed system model, so let's start with some specification of our model. So first we consider a single LTE cell, as we can see here. So we start by decomposing the LTE cell into discrete location or subcells. So we will have different subcells. We consider that we have only one user per subcell or per location. So each of these subcells contain only a single user. We consider that we have the same expected channel for all RBs within a single subcell or single location. And this is somehow realistic because we are talking on average. So the RB or the resource blocks of the LTE will be spread over all the bandwidths. And on average, they will have the same value. We consider that one user may have more than one resource block. So if a channel is weak, and we can propose to give more than one resource block in order to attain a minimum bit rate, and so we can consider that the sub cell is covered. We consider that we have no interference between users within the same cell, and also we consider that we have no interference in between cells. Of course, each user must have a minimum bit rate. If not, we consider that the location or the subcell is not covered. This is a system model. So this is the optimization procedure that we are going to implement, or we propose to implement. So we start with some fixed design parameters. So these design parameters concern the total power, the minimum bit rate, the noise variance, and the user densities. So using these fixed bit rates, we are going to optimize the capacity, the total capacity of the system over the power and the number of resource blocks. So the power, how much power we are going to give for each resource block over each subcells or each location. And n is here is a vector representing the number of resource blocks per subcells or per location. After doing the optimization, we are going to test if the constraints on the minimum bit rate are met. If yes, we continue. If no, we are going to remove the subcell or the location from the optimization procedure, and we are going to redo the optimization without the specific subcell. If the constraints are met, we are going to see if the coverage constraints are satisfied. So for maximum coverage, we must have resource blocks over all locations or over all subcells. If this constraint is not satisfied, we are going to save the results, and then we are going to change the design parameter and redo the whole thing. At the end, we have to do a compromise between different saved results here. So for the optimization problem, we have to maximize the capacity. So this equation here represents the capacity, so the total capacity over all the cell and over all the locations or subcells. So here CR, it's a vector. Each element of this vector represents the capacity within a subcell. And the capacity is given as Shannon capacity provided by this formula, where L is the number of sub-channels and B is the bandwidth of each sub-channel. So the capacity per subcell or per location is equal CIR multiplied by the number of resource blocks provided for each location. P here is a vector representing the power allocated for each resource block, N is the number of resource blocks per location, and here Rmin is the minimum bit rate, and here we have a constraint over the total power that can be used. Rho here is a coefficient that tell us about the density of users in the network. We have a constraint as well on the number of resource blocks that can be used per subcells or per location. Here AI is a parameter. So using this parameter, we can say that if a capacity does not meet the minimum required bit rate, it's going to be put as 0, so we can remove it from the optimization. So we can see that we have a mixed integer and nonlinear optimization. As you can see, we have log here, and the number of resource block must be integers. So this is a complex optimization, and using global optimization techniques can be cumbersome. So we propose to use a genetic algorithm as a benchmark, as genetic algorithms are known to have some global optimization properties. And we are going to propose a suboptimal approach where the optimization can be done separately over N and P's. So for N, we are going to use some heuristic algorithm to find the number of resource blocks per subcells. And as for P, we can do the optimization using known techniques such as iterative water filling algorithm. For the implementation, so here we are focusing on the optimization done in this block here. So we have two techniques, the genetic algorithm and the suboptimal approach. For the genetic algorithm, so we are, it's a heuristic algorithm and can be used for mixed integer nonlinear problem. So it's a benchmark, so we are going to compare the genetic algorithm with the suboptimal approach. And it can be considered as benchmark as it's known for some global optimization capabilities. The parameters used for the genetic algorithm, so the parameters are stochastic uniform selection, scattered crossover, and Gaussian mutation. For the suboptimal approach, we are going to implement a two-step solution. So in the first step, we are going to distribute the resource blocks over the different locations or subcells in a heuristic manner. So first, we are going to increase the resource blocks for location where the minimum bit rate is not satisfied. However, if we increase the resource block to a maximum number and the minimal bit rate is not achieved, we are going to remove this location or subcell from the optimization problem. So once removed, the allocated resource block for this location will be distributed over other locations, and this distribution is done in order to increase the capacity of the overall system. In the first step, we updated the number of resource blocks per location. For the second step, we are going to consider that the number of resource blocks is now constant, and we are going to update the power per resource block over all the location. This update is done using the known water filling algorithm technique. So for the result of the simulation, so we are going to test the proposed approach using these parameters. So for the total power, we have 2 watt. For the noise variance, minus 40 dB watt. The user density parameter is considered to be 0.5. The minimum bit rate 1.5 megabit per second. The cell radius is 1 kilometer, and the maximum RB per user or per location is 5. For the channel model, we consider a path loss model, a log normal path loss model. So we have some Gaussian distribution in dB around a certain average, and the average is obtained using the mobile environment path loss model. So we have an exponent gamma equal 4. The simulation is done using Monte Carlo simulation, so we are going to do the optimization over several simulations in order to obtain a consistent numerical results. So now we are going to show the results for both coverage and for the capacity by fixing some of the design parameter and varying others. So for the first simulation, we fixed the total power, the minimum rate, and the user density parameter rho, and we varied the noise variance. So for the coverage, the plot here shows a number of locations that were not covered. So in this case, we can see that the genetic algorithm did not perform well. So the number of uncovered area are much greater in genetic algorithm when compared with the water filling algorithm. However, from a capacity point of view, we can see that the genetic algorithm outperforms the water filling algorithm. So here we have a trade-off to be done, greater capacity or more coverage. Now, changing the minimum bit rate. So if we change the minimum bit rate, we can see that for a bit rate that is less than 2 megabit per second, the coverage using the water filling is better. And above the 2 megabit per second, we have that the genetic algorithm is outperforming the water filling from a coverage point of view. As for the capacity, so we can see that the genetic algorithm outperforms the water filling algorithm for all the minimum bitrate values. Now varying the user density parameter rho. So in this case, we can see that the water filling based algorithm is outperforming the genetic algorithm as long as rho is less than 0.9. As for the capacity, both algorithms gave almost similar results. As a conclusion, in this paper we proposed a static optimization framework that is aimed at maximizing the cell capacity and at increasing the coverage of a private LTE network. The private nature of the network makes it possible to know the user location and to use the expected channel gain at this specific location in order to perform the optimization. To solve the optimization problem, two algorithms were proposed and implemented. One algorithm that is based on genetic algorithm and a suboptimal algorithm based on water filling. The reported numerical results indicate the efficacy of both approaches with significant complexity reduction using the water filling algorithm with minimal performance reduction. As for future work, the interference from neighboring cell will be incorporated in the optimization problem. Furthermore, dynamic channel models will be tested and used, and a dynamic real-time optimization technique will be studied. Thank you for listening.